Hello everybody, welcome back to this series on trigonometry with college algebra. We will continue our talk of the college algebra portion today, so we'll get into it. Today we're talking about rates of change and behavior of graphs, specifically talking about increasing, decreasing, and constant intervals, both on a graph and from an equation. We'll be looking at finding both local and absolute maximums and minimum values, and also looking at finding the average rate of change over an interval. So on the first page here, we have a bit more of an intuitive side of definitions for increasing, decreasing, and constant behavior. And I think that there are hopefully no surprises here, that as we look at function inputs moving from left to right, so if we're looking at these input values moving from left to right, well, is the function value also increasing as it moves from left to right? Is it decreasing, moving down as it moves from left to right? Or is it staying the same as it moves from left to right? So as we look here, we see that as we move from left to right, that starting even down at negative infinity, as we move to the left, this function is moving up further and further and further until it gets to the input at -2. So if we're looking here, we can see that the first interval that we have of an increasing function is going from negative infinity all the way to -2. And again, we're using the open interval notation here. We're not going to be including the endpoints. From there, this thing starts to turn around and come back down. So we'll kind of put this all together at the end maybe, but hopefully we can see that from -2, from -2 to 0, we have a decreasing interval. As we're moving from left to right, the inputs are getting bigger, the function outputs are getting smaller on this interval here. And then from 0 to 4, we see that all of the outputs are exactly the same. As the inputs are getting bigger, the outputs are staying exactly the same. There is no change. They are all constant. So we can see that we have a constant interval here going from 0 to 4. And then it begins increasing again. As we move from left to right, these function values are getting larger and larger and larger off the screen. So that gives us another increasing interval from 4 to positive infinity. And then we would union those intervals together just to kind of turn that into one big interval, since we have these disjoint intervals where this function is increasing. The way that we join them together is with this union symbol. So hopefully the idea here is somewhat intuitive, that as the function inputs move from left to right and get larger, so left to right on a graph, but as they get larger, is the function value also getting larger? Well, it's increasing. If the function value is getting smaller, well, then it's decreasing. If the function value isn't changing, then it's staying the same. In this next page here, we will look at some mathier definitions, as I like to say, but these are more formal definitions here. So we say a function f is an increasing function, and we're always looking on an open interval, if f of b is bigger than f of a, so that function value at b is bigger than f of a, for any two input values a and b in the given interval where b is bigger than a. So like I said, that's a very mathy definition, but what it is saying here is that if we pick two values on some open interval, so I'm looking specifically, since we kind of know where to start here, based on our previous work, that we know it's increasing just by the way that the graph looks intuitively. But if I pick any two values in here, so maybe I pick -4 as one of my values, and I pick -3 at one of my values, well, the output at -4 appears to be about 0, and the output at -3 appears to be, I don't know, 10 or 11, or something close to there. So what we have is that -3 is bigger than -4, and we also have that f of -3 is bigger than f of -4. Now I picked two very specific values in there, but hopefully it's not too far of a stretch to see that any values that I picked in that open interval from negative infinity to -2 will have that condition, where if I pick two values where b is bigger than a, then f of b is bigger than f of a. And this is a way that we can use math notation to see when these functions are increasing or decreasing or being constant, and that will have some value to us later on. So I was just kind of writing some stuff down here, but hopefully we can still see that this increasing interval is going from negative infinity to -2. Same thing over on this side here. So we'll just keep talking about the increasing portion. I didn't want to select that value, but you can see if I pick two values here, here's a to the left, b slightly to the right, and if I call this value a and this value b, we can see that b is bigger than a, and also f of b is larger than f of a. So we also have the increasing portion on that side. So let me include that here as well. This is going from 4 to positive infinity. And let me just move some of this, scoot that over. Maybe put a little separator there, visual separator. But as we were talking about, whoops, this would be like my b value, that's my a value. This would be f of b being bigger than f of a. All right, so we can do that same thing for, well, let's keep that where it was. We can do that same thing for the decreasing interval here. So let me just wipe this a little clean. And we can think about this decreasing interval. So, you know, like before, we noticed that just intuitively we can see that going from -2 to 0, we can just like physically see that those values are getting smaller. Those function values are getting smaller as the inputs are getting larger. So, you know, I could pick some values in here as well. We could make this a, and we could make this b. So b here is definitely larger. Whoops, let me make that a little better. Definitely larger than a. And if I map them up here, we can see that f of a is now larger than f of b. So here we have that, f of a is larger than f of b, which is the same thing that this says. I wrote that the other way with f of b coming second, but those say the same thing there. And then lastly on this, this last interval here where things are staying the same, we can pick any two values there, you know, as things are getting larger. So here's 1, here's 3 to use some examples here. So 3 definitely larger than 1, but here we have that f of 1 is equal to f of 3. So as things are getting bigger, the function values are staying exactly the same. So there we have a constant interval. So maybe nothing too surprising there, but thinking about it using these kind of notations of, is the function value going up as the inputs are going up? Is the function value getting smaller as it's moving large, if the inputs are moving larger, or are they staying the same? Okay, so next we'll look at the local maxima, minima and maxima. So as you notice, we were kind of taking open intervals and ignoring the endpoints here. Well, there's something that is special that's happening at some of these endpoints here, and that's where we're getting some of these maxima and minima. So the graph here is slightly different than the one before. I removed the constant section and kind of made this more of a nice smooth curve. But what this says is that a function f has a local maximum at some value x equals b if there exists an interval AC with a being less than c, a being less than b being less than c, such that for any x in the interval from a to c, f of x is less than or equal than f of b. It's just such a complicated mathy thing to say, but it says precisely what we want it to say to talk about a local maximum. So if I look at this value here, so here my b value, my x equals b, I'm looking at -2. Let me just make some interval around it. So, you know, maybe it just goes from here to here. So that's what, like 3.5-ish to -3.5 to -1.5-ish. So that is kind of this open interval that I'm looking at here. So if I map those up, then I'm looking specifically at this region here. And I'm trying to highlight in green. So again, if we focus our attention on the B point, so what this is saying is if I pick any other x in here. So it could be here, it could be here, it could be down here, it could be down over here. All of these values, all of these function values are less than f of negative 2. This is the largest in that interval. So that must be a maximum point. So what we see here is that there is a local maximum, and I'm talking about just in this little interval here from negative 3.5 to 1.5, there is a local maximum at x equals negative 2. Now the local maximum value, if I map it across, and I tried to highlight it on here, that it goes right about to 16. So the local maximum value is at f of x equals 16. So that is one thing that it can be a little bit confusing, is when it wants to know where the maximum or minimum is at, we're talking about the input value. And when we want to know what that maximum value or minimum value is, we are talking about the output value. So similar story for local minima. Maybe I'll just change colors here for fun. But now I could still maybe create an open interval kind of around this spot where I'm claiming there might be a local minimum. So again, if I kind of map these down to my graph here, we're looking at this area right here. And we notice that if we pick any other value in here, oh, that's not very visible. Let me go back to this one. It could be here, it could be over here, it could be very close here, it could be very close on this side. But all of these other values I'm picking are all larger than the b value that we're picking here, which here we're looking at that being 2, and this function value being at f of 2. So same kind of story here. If we're looking for what this local minimum value is, it will be at x equals now positive 2, because we're on the positive side here. And the local minimum value is going to be f of 2, which is negative 16 in this case. And I guess I could have written f of negative 2 up here as well, just to keep things kind of more consistent. But the local maximum is at x equals negative 2. The local maximum value is f of negative 2 is equal to 16. That is the output value. And then the minimum is at x equals 2. And the minimum value is at negative 16. So, I mean, like I said, there's very mathy things going on here in terms of the definition, but hopefully it's intuitive that you can see like where these graphs are turning around and peaking out is when we can tell that that is either a maximum value or a minimum value. Looking at the graph, it's really easy to spot. What we're going to want to use these definitions for is when we're just given an equation or a function or something like that, and we want to use that to find these values. So next we'll talk about absolute minima and maxima. So what we had talked about on that previous page was local, meaning we're going to look at some interval, and is there a spot where it peaks out higher than everywhere else? Is there a spot where it dips out lower than everywhere else? So that's just looking at a local spot where that's happening. When we're looking at absolute minima and maxima, we're looking at the entire function. And we want to know that compared to every value in the domain, is there a spot where it attains some highest value? Is there a spot where it attains some lowest value? So a function f has an absolute maximum at x equals c if f of c is bigger than f of x for all x in the domain of f. So not just for every value in some open interval, but for every value in the entire domain of the function. So if I'm looking for an absolute maxima here, or maximum, since there's just one, we can see over here all the way to the right, we have some value that is very large, larger than anywhere else on this graph. So this tells us that the absolute maximum is at x equals 4, and the absolute maximum value is at 3. So f of 4 equals 3. And if we're looking for a minimum value, I don't know, I mean, I guess what I'm saying is don't be tricked by just looking at the other end here. Look for where this is truly the lowest, which is actually going to be down here at x equals 2. We are, that is the spot, that is the input where we're hitting the lowest value in this entire function. And then that value of f of 2 is equal to -1 in this case. So again, where we're finding where it's at is the input value, and then when we want to know the actual function value is what the maximum or minimum values are. All right, so next up is average rate of change. This idea will become increasingly important as you get into pre-calculus and even more important as you get into calculus. But the average rate of change describes how an output quantity changes relative to the change in the input quantity. So we have a bit more of a definition here. The average rate of change between two input values is the total change of the function values divided by the change in the input value. So we're just looking at this ratio. How much is the output changing over how much is the input changing? So here we have a nice way to write that. Delta y over delta x. This means the change in the y values, the change in the outputs, the change in how much this function is moving up and down, compared to delta x, the change in the x values, the change in the x values, compared to how much this thing is moving from left to right. And we have a formula to do that. Here's just like literally a couple of points where we're looking at the output values over the input values. And you see that everything lines up nice. So if we put the x2 value first as the function value, then we better put the x2 input value first as well. And if we're going to subtract the f of x1 function value, then we will want to subtract the x1 input value after as well. So what I'm trying to say is that this is also the same as f of x1 minus f of x2 over x1 minus x2. The order that we plug in these points doesn't matter, but keeping them consistent is what matters. Note this is the slope of the secant line connecting the points x1 f of x1 and x2 f of x2. So this should look very much like the definition of finding a slope, or the formula for finding a slope. So if we're looking at this example here, we're looking at the average rate of change on the interval from -1, and here we do have a closed interval because we do want to look precisely at the endpoints, so we do need to include them. But we're looking at this interval from -1 to +2. So we're looking on this interval here, and we want to know how much is this function changing on average between this point at -1. So if we look up here, we've got that f of -1 is equal to 4. And if we look over here at 2, we see that f of 2 is equal to 1. So now, putting this together, I want to look at the change in the function outputs. That's what goes in the numerator of this quotient here. So if I look at f of -1 minus f of 2 over -1 minus 2. And then we can simplify from here. F of -1 we discovered was 4. F of +2 is 1, and this is all over -3. So what we've got here is 3 over -3, which is -1. So the average rate of change over this interval from -1 to +2 is also the slope of that line that I just drew, connecting those two, which is -1. So using this average rate of change will be helpful in solving application problems, and it also, like I said earlier, becomes increasingly important as we get into calculus. Okay, so we're doing the same thing here, finding the average rate of change, but instead of looking at a graph and being able to quickly see what the input and output values are, well, we'll still know the inputs because it's given to us here in the problem, but we're going to have to go find those outputs more algebraically by plugging them into this function here rather than just getting them quickly from a graph. So that's the first thing that we're going to do here. Maybe we even know that if once I'm looking for my average rate of change, I'm going to have maybe 4 minus 2 in the denominator, and I want to get f of 4 minus f of 2 in the numerator. But I don't quite know what f of 4 and f of 2 are, so we'll go plug them into the function here and we will find out. So looking at f of 4, this is going to give us 4 squared minus 1 over 4, which is going to give us 16 minus 1 over 4. If I get a common denominator here, meaning I want to get a 4 worked into the denominator of this 16, but if I do anything other than multiply 16 by some form of 1, I would change the value. So that 4 over 4 is just multiplying it by 1, so I can get a common denominator. 4 times 16 is going to give me 32, 64. 64 over 4 minus 1 over 4 is going to give me 63 over 4. So there we've got that there. I'm just going to go create some space because I'm going to need it for this problem. But now that I've got it solved, let me just kind of clear that first step out of the way. And I will rewrite that f of 4 is equal to 63 over 4. And I will go make some space. All right, the next thing we want to find here is what f, I need a color here, what f of 2 is. So we will do the same thing by plugging it in here, and we're going to get 2 squared minus 1 over 2, which is going to give me 4 minus 1 over 2. I want to do the same thing of getting a common denominator so that I can subtract this fraction here. So I need to get a 2 in the denominator, which means I also need to put 1 in the numerator. So that's going to give me 8 over 2 minus 1 over 2, which gives me 7 over 2. So let's get that written down here as well. Now I know that f of 2 is equal to 7 over 2. All right, we'll make some more space here. I think I might have got that 4 by accident. All right, so now we can just plug things into what we know our rate of change formula to be. So we're going to have 63 over 4 minus 7 over 2 all over 4 minus 2, which is 2. But I think our focus right now is on the numerator. We're going to need to get common denominator again. So in order to turn the denominator on the right, the 7 halves, we need to get a 4. So we'll multiply by 2 over 2. That's just our convenient form of 1. So we're not changing the value of anything. We're just changing the way it looks. So then in my next step, I'm going to have 63 over 4 minus 14 over 4 all over 2, which is going to give me, let's see, 63 minus 14, 53, 49 over 4 all over 2, which is going to give me 49 over 8. So there we go. We know that the average rate of change, without being able to look at the graph here, from 2 to 4 is going to be 49 over 8, which is a positive number. So we've got a positive slope here. We know it'll look something going uphill from left to right. So there we go. There's our average rate of change using just a function equation. All right, with that, I will leave you to practice. Good luck, and if you want to see more of this, let me know.